Alright, welcome to this presentation on FTC hardware basics. Basically what I'm going to cover in this video is a lot of the common parts that you'll see on standard FTC robots in competition. And I'm primarily going to focus on the Tetrix robotics kit, which you can buy on their website, but I'll also go a little bit into some custom extrusion modeling for teams that might be looking into making more custom-built robots. And so starting off, I'm going to define a couple terms. So Tetrix versus extrusion, right? Tetrix is a kit developed by a company called Pitsco. And what it is it's an FTC approved kit that allows you to build robots. It's pretty simple. It's actually quite a nice kit. I've seen some really great teams that are using Tetrix robots, so it doesn't really inhibit you from anything. But a lot of teams at a certain level will transfer to what's called extrusion. So extrusion is a long metal bar. You'll see pictures of it later. And what it is it's the basic frame for a completely custom-built robot, because obviously extrusion is not a kit part. It's literally a metal bar with a slot in it to put nuts for screws. And so teams that want more custom-built robots, that want more flexibility in their building, might lean towards making an extrusion robot. And then the last term I want to define is a drivetrain or a chassis. And what that is that's the base of your robot. That's essentially the four wheels you have, your motors, the metal parts that connect those four wheels. It's just the very foundation of every robot. Alright, so let's start talking about some basic Tetrix pieces. So first you have a C channel. This is literally the most fundamental part of the Tetrix kit. It's what, if you're using the Tetrix kit, it's what you're going to build your entire robot out of. And they come in different lengths. This is one of the shorter ones because it fit my camera frame. The C channel here has some different hole patterns, right? You have an 8-hole pattern, and then you have a 4-hole pattern, some longer holes for axles, and it's just a super flexible piece of material that allows you to do a ton of different things, mount a ton of different things off of it. You have a Tetrix plate, so this is same hole pattern as C channel with the 8 holes, but it's a flat form, so for different purposes, obviously. You have a bracket, so this is often used for mounting motors. We'll go into that a little bit more later, but same idea as like a flat plate. A C bracket, this allows you to create perpendicular facing objects. So if you think about a drivetrain, right, you have 4 wheels, probably like a square kind of configuration on top, but then to get this square you need 90-degree angles, and so this is a really great way to get those 90-degree angles. You have a corner bracket, same thing as the C bracket, just rectangular. And we have this flat bar, so this is less of a high quality photo, but it's a similar idea to a Tetrix flat plate, except it's really thin. It just has one hole spanning it, and so you can mount things off of a flatter, thinner bar. You have a standoff. So standoffs are really interesting because they look a bit like this, and they actually have threaded holes on both sides of it for screws to go into. And so what you can do with a standoff is you can actually have screws facing each other, and so you can almost mount like 2 different plates or really anything off of both sides of it. Almost acts as like a spacer as well. Now we're going to go into basic extrusion pieces, just so you can get an idea of the difference between the basic Tetrix pieces and basic extrusion. So here's the extrusion pieces I was talking about. There's 2 different sizes up here on the screen. So the larger one on the left is a 20mm extrusion, the one on the right is 15mm. And so both have essentially the same functionality, where you can see these little slots in the side that you would be sliding nuts into, and then you'd be able to mount things on top of the nuts and then screw it in. Both of these use different types of screws and slightly different hardware sometimes, just if you consider the size of the slot, obviously it's a little bit different. So the reason I put these both up here so I can go into that a little bit later. We have an L gusset, and this is where sort of those different hole sizes come in. So both of these are shaped like L's, as you can see, obviously. Same idea, being able to mount things at a 90-degree angle, because you put one extrusion bar maybe this way, one this way, or really however you want it. This one is for the 20mm extrusion. You can see the hole size is a little bit bigger. This is for 15mm. We'll go into what kind of screws mount into these very soon, but these are the L brackets, or L gussets. These are angular gussets, so the same as the L gussets, the one on the left for the 20mm extrusion, but there are a ton of different angles that these come in, so if you want your pieces mounted at an angle, this is what you would go to. You have a triangle gusset. So this is specifically for the 20mm extrusion. It is almost identical in functionality to the C bracket, if you remember from the Tetrix pieces, where you can mount two parts perfectly perpendicular. So you have one going this way, one going up this way. You can also use an L gusset if you use it on both sides of the material, kind of secure it, but this is a really small, compact way to do it. Now we're going to go into wheels. So obviously you guys know what wheels are. There's a ton of different kinds you can use though. This is a very, very basic standard tank wheel. And so this allows you to just move forward and backwards, very simple. It requires little to no extra programming, or really it's very, very simple. You have an omni wheel, and so you can see it has these little roller wheels on the sides. And so what this allows your robot to do is that if it is turning, it can actually turn on these little rollers. But the really nice thing about an omni wheel is that if you choose to power one wheel faster than the one on the other side, so it's turning, right, because one's going a little bit faster, then the one that's not being powered, that might be moving a little bit angularly, will actually be rolling on these roller wheels. So it's a really, really smooth way to turn your robot. And this is a very popular option for a lot of teams. Now you have this Mechnum wheel. So this wheel looks a little funky, right? All these rollers are going actually at 45-degree angles. And obviously this seems very impractical, because what kind of robot wants to go to 45-degree angle? But the brilliance of a Mechnum wheel lies in math. So if you think about vectors, which are essentially just lines at different angles, if you have two lines that are going at 45-degree angles to each other, so one maybe going this way, one going this way, then they actually would cancel each other out and go upwards in a straight line. And so what a Mechnum wheel does is it uses the different angles of all these wheels to cancel each other out and create linear motion. But the fact that these are all at 45-degree angles, you're canceling all these different lines, all these vectors, you can actually have your robot move in any lateral direction. So if you want your robot to move at a 45-degree angle to the top right, like the northeast, I guess, it can do that. If you want it to move at a 30-degree angle to the southwest, it can do that. And so Mechnum wheels are a lot more complex to code, because obviously you're doing all this cancellation and whatnot, but they're really, really powerful and really useful for the majority of robotics games. Now these all-terrain wheels, these are a little bit... Now we have these all-terrain wheels, so these are quite interesting wheels. They're these big foam wheels, and the idea about them is that if they have to roll over any debris on the field, they can do that really, really easily. These are generally not super practical. If you look at it, there's no hole pattern in here. You actually have to make a custom mount for it and using some kind of CAD software. And they are pretty big and clunky, but that doesn't mean that they're not ever going to be useful. It's just an option you might want to keep in the back of your head somewhere. Now I have these compliant wheels, and so I put them in the wheel category because they are, by definition, wheels, but you don't actually want to use compliant wheels for your drivetrain. So compliant wheels are these little squishy rubber wheels. You see two different kinds up here. This one's actually a lot smaller, zoomed in, and a lot squishier than this one. A little bit more rigid, a little bit bigger. And what compliant wheels are really, really great for the majority of the time, is for what's called an intake. So what an intake is it's some kind of mechanism that sucks an object into the robot. So if you're thinking about maybe to stack some blocks, you might want to suck in a block, and then carry it, and then stack it on top of something. And so compliant wheels, because they're squishy, they're able to grab onto that material from two different sides and then roll it in. And so these would be the kind of wheels you'd want to use if you're building an intake. You put some motors on them, make them spin really fast, and they'll suck in a whole bunch of different things. Now we're going to move on to other pieces you might need for your drivetrain. So first we have axles. You see two different kinds of axles here. We have a D shaft, because it's a bit flat here, rounder here, looks a bit like a D, and a hex shaft. And so these are two different kinds of axles, obviously. They require different parts to mount them. Generally, a hex shaft is considered more preferable just because it doesn't have this little smooth side that can slip out sometimes, but D shafts are super secure too. I know of some really, really great motors that use D shafts and hex shafts. Just know that they require different types of mounting pieces. Now, whether you're using Tetrix or extrusion or anything, that's not going to limit the kind of axle you can use. What might possibly change that is actually the kind of motor that you use. So I'll get into that later. But motors can have D shaft axles or hex shaft axles mounted to them, just depending on what kind of motor you buy. So motor mount, kind of going into that category, This is a very standard motor mount. So it has this 6-hole pattern here that screws into the front of the motor, and then this little round part that just slips onto the back of the motor. And so what this allows you to do, and this is primarily for actually extrusion systems, is that you can slip a bar of extrusion in between this plate and this plate, and then because your motor is mounted on both of these, it just stays super stable. So I'll actually go into what the Tetrix motor mount is soon, but here you can see that motor assembled, so the bar of extrusion would go right here in the center area, and your motor would be mounted. So this is what a Tetrix motor mount looks like. It's a lot simpler. What it basically has is this set screw right here. So you stick the motor, you make the screw really loose, you stick the motor in, and then you make the screw really, really tight. And so it essentially clamps onto your motor, and then you just mount this part, there's some screws on it, to whatever your piece of Tetrix is, and then your motor stays on there. And so if you're using a Tetrix-based system, highly recommend this motor. Now here's an axle hub. This one's specifically for a hex shaft. You can see the little hexagon pattern right here. And what this does is it allows you to mount an axle to something. So you have these, there's a little rod right here you can see, there's one on this side as well. You can stick that into 2 holes and then bring a screw from the other side into this. And so now that you have things going in from both sides of whatever you're mounting it to, it stays on secure and your axle can go through. And here's a shaft collar. What this does is it secures the position of your axle. So if you have this, and you screw it in the way I just explained it, the axle hub will be very secure, but the axle itself can move within it, right? There's nothing holding it down. But what this has, and you can't really see it in this picture, is there's a really tiny set screw on the other side of it. And so when you stick an axle through it, you tighten the set screw pushes into the axle and then just keeps it jammed in there. And so there's different types of shaft collars for D shaft and hex shaft. They essentially look the same, they're just different sizes, so make sure you're getting the right kind if you're working with one versus the other. And now we have spacers. So these are again for hex shafts. There are spacers for D shaft, but they just didn't have them on hand at the time. You see that there's all these different sizes of spacers. What these do is, as you can probably tell by the name, they give you space on your axle. And so let's say that you use an axle hub and you mount an axle to a flat piece of metal somewhere. And now you need to mount something else off of that axle, but you need it to be, let's say, 2 inches away from that flat piece of metal, and you have nothing in between. Well, obviously, if you just try to screw it on 2 inches away, it might kind of slide around, might fall all the way back. You put a spacer there, it won't be able to. It'll be blocked by the spacer. So these are really, really useful for if you have precise measurements you're working with or you need a certain distance for things. Now I'll go into motion. So what motion is we're going to be talking about things like motors and servos, things that just make your robot move. So first off, here's a very standard motor. This is created by a company called Rev Robotics. It's the HD hex motor. So hex refers to this hex shaft, as we talked about earlier. This is what a lot of motors are going to look like. So you can't see it in the picture again, but there's that 6-hole pattern that we had seen in some of the motor mounts earlier. And then this is just a very standard motor. Obviously, you plug it in, all the cabling's up here in the back, and it spins. One thing to keep in mind about motors is that there are different types of gearboxes. So what a gearbox is it's this front part over here, and different gearboxes have different gear ratios. So depending on what the ratio is of the gears in the gearbox, your motor will be at a different speed. So this one says 40-1. This is generally a very mid-range motor in terms of speed. The 3 standard ones are 20-1, a 40-1, or a 60-1. So 60-1 is the slowest kind, but it has the most torque, so torque is like strength in a way. And the 20-1 is the fastest of those 3, but it has very little torque. You can find some motors that go as small as like a 3-1, and some that go much higher than a 60-1, just depending on what kind of specialty retailer you're getting it from and what kind of purpose you need it for. But generally, a 20, 40, or 60 will serve you just fine. Now there's also these servos. So the difference between a motor and a servo is really just the strength and the speed and the function of the thing. So servos also rotate circularly, just like the motor did, except a lot of servos have limited ranges of motion. So you might have a 90-degree servo, which means it can rotate 90 degrees, then it gets stuck, has to rotate back in the opposite direction 90 degrees. Servos also have a lot less torque and a lot less speed than motors, so they're used generally for smaller functions. But the reason why teams use servos is because in FTC we have a cap on the number of motors and servos we can use. So you can use a total of 8 motors on your robot and 12 servos. And so obviously servos become a very popular option for doing very small things on your robot, just because you have more of them that you can use, and then you're not using up your valuable motors that you might need more for your drivetrain or heavy duty functions. So this is called a servo block. It's missing a couple screws up here, but the purpose of a servo block is to create kind of an encasing or for the servo so that you can screw it into the rest of your robot. One thing that's missing here is called a servo horn. And so that's the part that would go from this little plastic nub of the servo to create a whole hole pattern that you can mount things off of. But these screws on the side are really what's going to help you mount your servo to whatever you need to be mounted to. So these are the servo horns I was just talking about. These go into the plastic parts of the servo here, and then create these hole patterns that you can then mount objects off of. And so if you have a servo horn on your servo, kind of looks like this, there'll actually be a set screw inside of here. So it's a really, really tiny screw that when you stick it through and you tighten it, it secures the servo horn to the servo so it doesn't fall off. Now there's another kind of servo. This is the one we were just looking at. This is called a quarter scale. So this is just a really, really big, really, really powerful servo. It still counts as one of your 12 servos in FTC. It's just a little bit bigger. So it's not necessarily super necessary for a lot of purposes. It's also not any faster. It's just more torque. But some teams like to use quarter scale servos if they need a slightly more heavy duty function, but not so much that they need a motor. One thing to note about quarter scales is they will require a different servo mount just because they are bigger. Now we have gears. So gears allow you to transfer motion from your motors, or sometimes even your servos, to other parts of your robot. This is a very standard set of gears. You can see they come in different sizes. They have your 4-hole pattern here, so you can really attach it to a lot of different things. And from this point, I want to talk a little bit about what gear ratios are. So gear ratios refer to what scale your motion is put through when it's sent from your motor to the final place where it's rotating something. So let's say I put a motor onto this little gear, and then it's attached to just this one. Ignore this one for now. So obviously this tiny little gear, with one full rotation of the motor, it's going to be able to climb this many gears up on this thing, this larger gear here. But because this larger gear has more little teeth on it than this one does, one full rotation of the motor will not fully rotate this gear. And so your gear ratio is going to be less than 1. I don't quite know the number of teeth on these, but it's going to be whatever the number of teeth is on this one divided by the number of teeth on this output. However, you flip it, you put a motor on this one, and then you're trying to spin this one. What you're going to end up with is, when this thing fully rotates, it's going to have a lot of teeth that are going to go through this little tiny gear. So this gear is going to spin multiple times over, so your gear ratio is much larger than 1. And what this allows you to do is to take the motion you have from your motor and either make it faster with less torque or make it have more torque with less speed. And so if you're using, let's say, a 20-to-1 motor, but you want it to go a lot faster than that, what you'd want to do is put that 20-to-1 on this kind of gear, or maybe even this one, and then attach it to a smaller gear. So that smaller gear will move a lot faster. You'll get a lot more rotation out of it. And so gears can be put all next to each other. As you can see, there's 3 gears in a row right here. And so if you have a motor on, let's say, this one, it's going to spin this gear multiple times and then spin this gear a ton of times. And so the final output is not actually going to change. Just having more gears allows you to translate motion across much further distances. Now, these are what we call sprockets. So sprockets have the same gear ratio idea as the gears in the previous thing, but as you can see, the little teeth are a little bit bigger. So you might be wondering, well, why are they bigger? The sprockets are not just for directly meshing like this. As you can see, they don't quite sit well with each other. What sprockets are for is for mounting what's called chain. So chain also allows you to translate motion across a larger distance, create these kind of ratios, change your torque and speed. But it doesn't rely on the metal being able to directly mesh with each other. One issue a lot of teams will have is that their gears will not mesh perfectly if they don't mount it perfectly. And then if the gears are skipping a little bit, they start chipping away at each other. You're not getting the motion you want and you're breaking your parts. But with chain, if you get it mounted correctly, the chain is just going to keep spinning. It's going to be a very smooth motion. And so this is, as you can see, you have your chain on here, smaller sprocket here, larger sprocket here. And so if this one's moving, the chain is what's going to move your motion all the way to the sprocket. So you don't need the gears in the middle so you don't need anything in the middle like the gears would require, because this chain can translate the motion for you. So these are really, really useful, especially for things like drivetrains, where you might want to mount your motor in a different place than your actual wheel is, and so you want to translate that motion over. And so here we have what's called a worm gear. So worm gears are rarely used, if ever, but what they allow you to do is essentially take motion from a shaft and translate it at a 90-degree angle. Don't worry too much about these. You probably will never have to use them in FTC. So fasteners are ways that you can attach things, make sure that they're secure. This kind of nut is called a kept nut. And what kept nuts are used for are primarily the Tetrix build system. And so, as you can see, there's a little threaded hole here. That's where your screw is going to go in. You're able to fasten things using this kind of kept nut. And so here we have a Tetrix screw. It is an imperial screw if you kind of have an understanding of how your screws work. And it screws right into this kept nut over here. Now this is what's called a T-nut. So what a T-nut is for, it's for 20mm extrusion. So that's a larger piece of extrusion. And this is shaped so it slides into the extrusion bar. And then a screw like this, called an M5, if you are using the metric screw system. This is a 4.0 on your hex keys. And this kind of M5 can screw right into your T-nut. And now you have a countersunk M5. So you can see that this is the standard M5 from earlier. This is the countersunk one. So this is a flat head, while this is a little bit larger. And this is for if you need something to be flush, whether you're exceeding some kind of size limit, whether you just need a low profile on your screw. That's what you want to use. Now we have an M3. M3s are for your 15mm or your smaller extrusion bars. And the lock nut is similar to the M3 nut, except it has this little nylon inside of it. And what this does is that it actually reverses the threading of the nut inside of the nut. And so this prevents the screw from easily being able to unscrew itself. So lock nuts, in terms of their height, are actually a little bit higher, or actually a little bit taller than your standard M3 nut, but they really keep things on super securely. So if you have a screw that you really cannot afford to have maybe unscrew or get loosened a little bit, you want to use a lock nut. If you have a part you're going to be iterating a lot, maybe start off with an M3 nut, use a lock nut in the final product. Now this is your M3, so the M3 nut is for these kind of screws. So it's a 2.5 on your metric hex key set. It also has a different type of low profile screw called a button top. So instead of being a flat top, it's a little bit of a rounded dome type top, and it uses a 2.0 a metric hex key. And these are both for your 15mm extrusion, whether you need just a standard screw or a low profile. Now Phillips head screws, these ones you'll use less often. It's more used for the products you've already bought, like maybe a motor or a servo or other types of store-bought products. But a Phillips head can be quite useful sometimes. Obviously it has the iconic little cross in the center, requires a screwdriver, not a hex key, but you should know the standard name for this. We have a washer. So if you remember I said about spacers, is that they give you space on the axle so you can mount things at an offset distance from the beginning. A washer can do a similar function. It seems like it does a similar function, but it's actually not quite for that. So what a washer is for is that, let's say you have a really, really big hole in something, but you want to put a really small screw through it. Like let's say an M3, those are pretty small. Well, if you put an M3 in it, it's just going to fall through the hole, right? But if you use something like a washer, this larger outer diameter will fit on top of the hole, but then the smaller inner diameter will allow you to put a smaller screw through it without the screw falling through. And so these are really useful for when you have those larger holes but you want a smaller screw to go through. Now adhesives. So when you think of adhesives, you probably think about tape. That's pretty much what we're going to be talking about. So surprisingly enough, tape is going to be one of the most important tools you work with. Obviously, it should not be an intentional part of your design process, but inevitably, it solves a lot of temporary issues that might spring up at the last second or in competition, or just when you're iterating a design and you don't quite have the resources to fix something quite yet. So standard duct tape, we all know what duct tape is. It usually comes in kind of silver color, but it comes in all sorts of different colors for different purposes. It's very strong, very sticky. Don't recommend using this in your robot too much because the glue does melt into literally everything, but very useful, strong tape. Masking tape. Also don't recommend this on your robot because it's not very strong, but masking tape can be used a lot for creating a whole bunch of other things that you might need for your team. Electrical tape, now this is where we get into robot tape. So electrical tape is designed to resist really, really high temperatures. So if you're running electronics through it, it's not going to destroy the electronics or destroy itself. Electrical tape is really useful for not just electronics, also sometimes if something breaks down, it holds really, really well because it won't melt off. So I recommend if you need to fix a robot at competition, have some electrical tape on you. Gaffer tape. Now this is a little bit of pricier tape. It's not used for robots, but it is used in FTC. And that's because gaff tape is the standard tape that's used to tape the robotics field. So if you've ever seen a field diagram for an FTC robotics game, there'll generally be these red and these blue lines and squares going all over the field to represent different things. And gaff tape is generally what's used for that. So if you have your own field set up for your team, this is the kind of tape you want to get. VHB, this is personally my favorite kind of tape, followed very closely by electrical. But what VHB is it's a very, very powerful, almost foam-like double-sided tape. So the texture of it is kind of soft, kind of malleable, but it's really, really strong double-sided tape. And it's so hard to remove once you put it on, I have to say. But that actually makes it perfect for if you want to mount something to your robot. Again, I don't recommend taping things, but sometimes if you need to mount, let's say, a side plate. So what a side plate is it's usually some kind of acrylic or aluminum plate on the side of your robot that either acts purely for decoration or might, be hiding the jumbled mess of wires inside. And VHB has come in useful so many times for mounting that kind of thing. And it's another, if you're at competition, your robot's breaking down, look for VHB as well. Now, other miscellaneous items I want to go over that are going to be really important. We have the expansion hub. So the expansion hub is sometimes referred to as like the control hub. These are actually going to be replaced very soon by what's called a control hub. But the function's very, very similar, almost identical. So on the side of the expansion hub, these are some of the power plugs. You have 4 for motors. The encoder wires on the motors are going to go right next to those. You have servo plugs right here. You have some sensor plugs all the way down here. And so what this is it actually stores the information for all your code and all your controls, and then communicates to all the motors and the servos and the sensors about what they need to do, essentially. And so most teams will have 2 expansion hubs because, remember, we max out at 8 motors and 12 servos, and this can hold 6 servos and 4 motors, so math kind of works out there. We have the phone. So as of the 2019 to 2020 season, this is a legal phone for competition. I recommend checking Game Manual Part 1 every year that you're watching this just to make sure it still is legal. This is a Samsung Galaxy S5. But what the phone is it is your way to control the robot turning on and off when you're not directly plugging things in, flipping switches on your robot. And so when you're in competition, let's say, as I mentioned way previously, you have an autonomous section and a human-controlled section of the robot game. So to switch between those sections, you're going to have to use software on your phones. So FTC does have official software, so look into that when you're getting the phone for it, but you're definitely going to need one of these. Now you have an OTG cable. So what this does is it converts the micro USB to a USB. This is generally useful for your phones, whether on your robot or just for your control hub somewhere. So if you ever need something like that, look into this. It's a pretty useful and durable cable. And this is how it worked out in our on-the-robot phone mount for the 2018 to 2019 season. So we made this custom phone mount here. Your phone plugs in here. You're able to run the OTG up to here, and then use a USB to attach it to the expansion hub. And our reasoning for this was that it's better to keep plugging things out of this OTG than to keep plugging it out of the phone power port and then possibly damaging the port. So that's another use case for this that you might want to consider. Now here's a standard Tetrix 12-volt battery. Do you guys remember Tetrix? A great brand. Not sponsored video. But this is a battery that they've created that's legal for FTC competitions. It's very, very common, 12-volt battery. And every robot is going to require a battery to function. And so this is a really, really great option. I highly recommend using one of these. Now you have your controller. So, as I mentioned a ton of times, there's a human-controlled portion of the robot game. And to control the robot, obviously you can't touch it. So you have to use these kind of controllers. So this is a Logitech controller. This is the one that we use in MSET right now. But you can use a bunch of different controllers. Again, check out Game Manual Part 1. That has all the legal parts that you might need. And our controller is going to plug into this little hub over here. So what this hub has is it has multiple USB ports because you can actually have two drivers controlling your robot in competition. And so now you can have this one cable that might be running into the phone on your end so it can communicate with the robot, but then you can also have two controllers plugged into that. So this is also a really useful tool, and the controller is going to be required. Now surgical tubing, this is not like anything we have just discussed, but surgical tubing has become a very, very common part for teams to use recently. It's often used as a type of spring. Surgical tubing, it's this rubbery material, a little bit stretchy, but it does kind of work like a spring where it wants to come back to its standard at rest form. And so if you use surgical tubing, it can work to maybe resist motion a little bit to pull things back in. So let's say you have a motor to spin something out, but then you let the motor go. The surgical tubing will just pull whatever your object is back in. Now tread. This used to be a very common part in FRC, so the first robotics competition, as wheel tread, so to kind of allow the wheels to grip the ground better. But recently tread has actually been proven to be a pretty effective intake material. So if you remember, intakes are generally you have two compliant wheels that are able to suck things in. Tread also has that ability to kind of squish onto things and really suck them in. So you can also look into tread if you're trying to build an intake. Now we're going to talk a little bit about wiring. So there's a ton of different types of wires. If you remember the expansion hub, all the little ports on it were very different, and so you need different types of wires for them. So first let's start off with the servo wire. So the servos were those little weaker motors. These are the kind of wires you're going to need. Now a power pole is for a motor. So this plugs into the back of a motor. This plugs into the expansion hub. Super simple wire. Now a battery charger, not quite a wire, but also incredibly useful. This is a dual battery charger. And so if you remember, this is called a power pole down here. And so this plugs into the battery, and then you can control its charging up here so that you always have your batteries nice and juiced up. So this is a sensor. There are multiple different types of sensors that are out there. This is just one of them. But different types of sensors are available for things like detecting color, detecting distance, detecting if an object has been pushed, touch sensors, essentially. So if you need that extra level of autonomy, sensors are incredibly useful for that. So this is what a motor looks like when it's all wired up, ready to go. So if you remember this motor from earlier, you have the motor wire running, and then this is what's called an encoder wire. So it's a 4-pin wire that plugs into the motor and then plugs into your expansion hub. And what the encoder wire does is it counts the number of little tick marks that the axle of the motor has rotated and communicates that information back to the expansion hub. So if you want the robot motor to move, let's say, 20 ticks in one direction, then the encoder will communicate how many ticks have passed to the expansion hub, and then your code can allow the motor to stop after 20. And then this is just for communicating power to the motor so it can actually rotate. Now this is a type of wire that's used to connect your phone to your expansion hub. So again, this is from the 2019-2020 season. Control hubs are rolling out that will actually just not require this phone, that'll just be a hub here. But as of when I'm filming this, this is still the standard that we're using. And this uses a micro USB to plug into here and then a macro to plug into the expansion hub. And so this stores all the code on the phone and then communicates it to the expansion hub, which then passes it on to all the motors and servos. So this is a full setup, or at least one of each kind of thing. You have your phone plugged in here, your motor plugs into this side, your servo is going down in this bottom row, and then your sensor is going on this side part here. So if you remember looking at the blank expansion hub, I was explaining this, here it is visually. Now tools. Obviously you're going to require a lot of different tools to build your parts. We're going to go over those. You have a caliper. What a caliper does is it's a very, very precise type of ruler. So you're able to slide this part of it out, squish a piece in between here, and then jam this back in, and this will actually read, either millimeters or inches, depending which setting you choose, how long the object is. Similarly, this top part, you can't see it super well, but it actually has two little pointy things that are crisscrossed a little bit. And so this is for reading hole diameters. So if you stick it inside a hole and pull it apart, it reads the distance in between this part of it and then this part of the other one. And so this is a super useful tool for measuring things that already exist if you need to, say, cut apart or just understand how big something is. Here you have pliers. You've probably seen these before, but pliers are really great for grabbing onto things. That might be smaller, that might be a little bit harder to grab with your fingers. You have two types of pliers here, just some standard small pliers and then needle nose. So needle nose are just a little bit longer. So if you need to reach into a really small space, needle nose work, but these will be a little bit stronger. A monkey wrench, you've probably seen this too, but you just turn this little dial and the wrench goes in and out. Has the same function as pliers where it grabs onto things, but obviously a wrench is a lot more heavy duty. Now wire cutters are for doing exactly what it sounds like. This is a sharp little thing inside here. It's almost like a pair of scissors, and it cuts wires. Generally in FTC you're not doing a ton of electronics work. You might use these to cut zip ties a lot. But if you ever end up making wires, you're going to be using these to cut lengths of wire. Then you have snips. These are, again, glorified zip tie cutters. That's pretty much all I've ever used them for, but they also work for electronics work. Now hex keys, I've talked about these earlier in the presentation, but hex keys are how you screw in your Tetrix screws, your M5s, your M3s, all of those. And there's two different types of hex keys. You have imperial hex keys and you have metric. So metric run on numbers like your 2.5, which is M3, your 4.0 is M5, while imperial run on inch measurement. And so if you're going to be buying your own hex keys, you'll need to buy at least one of each set to have a complete collection. Now a ballpoint Tetrix driver, in MSET we jokingly call it the OP Tetrix hex key. It's a Tetrix hex key, that's what the hex key ball head measurement is here, but because of its increased length and this really nice handle, it actually gives you a little bit more torque, and so it's really, really nice for using hex keys. And then also, because of the ballpoint design here, it doesn't strip the hex key, so stripping means the little hexagon becomes more of a circle, so it doesn't actually do anything anymore, it's pretty useless. So these are really, really nice for that as well. Now, same idea, this is sometimes called the OPM3, exact same as the ballpoint Tetrix, but this one's just a 2.5 M3 hex key. Now Phillips head screwdrivers, you've probably used these before as well, but different sizes of screwdrivers for different purposes. Something that's this small might be used for taking apart a motor sometimes. Something one of these sizes might be used for actual Phillips head screws for doing larger build projects. Now nut drivers, these are not super well-known parts if you're not in the robotics world, but they are incredibly useful. So if you remember me talking about kep nuts and M3s specifically, they have a little bit of that hexagonal pattern. And so let's say that you're trying to screw in a screw into a nut. Now, after a certain point, the nut is going to start spinning with the screw if it's not tight enough, right? And so you're left with two options. Either you use a pair of pliers to try to hold that nut in, or you take one of these nut drivers. These nut drivers are actually fitted for those nuts. This will fit for an M3 hex key, or sorry, an M3 nut. This will fit for a Tetrix kep nut. And so you just stick it in there and then you screw your hex key and it works like a charm. It's so much easier than using pliers. And so if you have one of these, if you have the space in your robot, you can kind of stick it in. This will be so much easier than using pliers. And even chain breakers. If you remember from the sprocket section, chain is what's used with the sprocket. This allows you to break the chain and reform it to create the length that you need, because when using chain with sprockets, you actually need the chain to be the perfect length for those sprockets. Otherwise, a loose chain isn't going to rotate all the motion. Too tight a chain just isn't going to allow you to get the distance between the sprockets that you need. Here's like a box cutter knife. So this is useful for not quite metal, but for making maybe cuts or scored indentations on different parts. We have a hacksaw. It's pretty self-explanatory. It's for sawing metal parts. So if you have a C-channel, you need to be shorter. Just mark a little line on it and then hacksaw it, and you'll be able to cut it down. Scissors, hope you know what those are. Hammer, also pretty self-explanatory. Files, these are for smoothing out rough edges on metal. And so an actual rule in FTC competition, when you get your robot checked to make sure it's legal, is they'll check for sharp edges, because you don't want sharp edges on your robot, because those can cause injury really quickly. I have personally experienced an injury from sheet aluminum that was not filed correctly, and trust me when I say you don't want to feel the same way. So here we have two different kinds of files. We have this rectangular file. This is generally used for sheets of metal or C-channels or extrusion or whatever you're using to file down an edge. Here we have a rat tail file. This is a little bit more for holes because it's a cylindrical file. So different types of files, all sorts of different sizes you can get, but definitely make sure you file down everything. We have a clamp. This is for holding a part really tightly so that, let's say you're hacksawing it, the part doesn't just fall off or doesn't move around. It just stays where it needs to be. You can clamp objects to tables. That's the most common use of a clamp. Or you can even clamp two objects together if you need them to stick, if you put glue in between or whatever you did. We have a drill. Probably know what a drill is, but here you have your drill battery, and a battery charger. Drills have different things called drill bits, and so those allow you to create holes of different sizes. You just drill the hole in, and this is what the whole drill looks like assembled. So you've probably used a drill before, but again, safety is important, so make sure you're being safe while using a drill. And those are all the parts for FTC hardware. I know this was a much longer video, so thank you for sticking through it. If you ever need to reference this slideshow, the link will be in the description below. Otherwise, I'll see you in the next video.